A fault line runs quietly beneath one of North America's most iconic alpine lakes, its presence largely invisible, yet persistently measurable. How does a structure hidden below deep, clear water come to be labeled among the most dangerous in its region? What does it mean when geological records suggest a repeating pattern of powerful earthquakes spaced across thousands of years, and how close might the present day sit to the next rupture? Beneath the scenic calm of Lake Tahoe, a growing body of research is narrowing in on a feature that has long been mapped but only recently understood in sharper detail: the West Tahoe Dollar Point Fault. The fault traces along the western margin of the lake, extending roughly 25 miles or about 40 kilometers from near Emerald Bay toward Dollar Point on the northern shoreline. It forms part of a broader network of normal faults that define the Tahoe Basin, a structural depression shaped by crustal extension within the Basin and Range Province. This region is characterized by the stretching of the Earth's crust, producing alternating mountain ranges and basins over millions of years. Lake Tahoe itself occupies one of these basins. Its remarkable depth, more than 1,600 feet, or roughly 490 meters, linked directly to tectonic subsidence along faults like West Tahoe Dollar Point Fault. Recent studies have sharpened estimates of how this particular fault behaves over long time scales. Sediment cores extracted from the lake floor, combined with high-resolution bathymetric mapping, reveal evidence of repeated seismic disturbance. Layers of disturbed sediment, known as turbidites, appear in sequences that can be dated and correlated across different parts of the basin. These layers indicate episodes when strong shaking destabilized underwater slopes, sending sediment cascading into deeper sections of the lake. By counting and dating these deposits, researchers have reconstructed a timeline of past earthquakes associated with the fault system. The emerging pattern suggests that large magnitude events, those exceeding magnitude 7, have occurred on the West Tahoe Dollar Point Fault at intervals of approximately 2,000 to 3,000 years. This recurrence interval is not precise in the sense of a predictable clock, but it establishes a statistical framework. When combined with the elapsed time since the last major rupture, it allows for probabilistic estimates. Current assessments place the likelihood of a magnitude 7 or greater earthquake on this fault at roughly 3 to 4% within the next 50 years. While that percentage may appear modest at first glance, it is considered significant in seismic hazard analysis, particularly given the potential consequences. The geometry of the fault contributes to its capacity for generating strong earthquakes. As a normal fault, it accommodates vertical displacement, with one block of crust moving downward relative to the other. In the case of the Tahoe Basin, this motion has gradually deepened the lake over geological time. During a major seismic event, displacement along the fault could reach several feet or more than 1 meter, occurring abruptly over a rupture length spanning tens of miles. Such movement would release substantial energy, producing intense ground shaking not only beneath the lake, but across surrounding communities in both California and Nevada. The underwater setting introduces additional complexities. A rupture along the West Tahoe Dollar Point Fault has the potential to displace large volumes of water indirectly by triggering submarine landslides. Steep underwater slopes, built from accumulated sediment, can fail when shaken, generating waves within the confined basin. These waves, often described as seiche or localized tsunami-like oscillations, can travel across the lake and impact shorelines within minutes. Modeling studies indicate that wave heights could reach several feet or over 1 meter, depending on the scale and location of the triggering landslide. While not comparable to oceanic tsunamis, such waves would still pose risks to marinas, lakeside infrastructure, and low-lying areas. The focus on the West Tahoe Dollar Point Fault does not imply that it acts in isolation. Beneath Lake Tahoe lies a network of active and potentially active faults, each contributing to the region's seismic character. Among these is the State Line Fault, located near the southern end of the basin. This structure trends roughly north-south and has been associated with smaller magnitude earthquakes recorded in historical times. Its activity suggests ongoing deformation in the southern portion of the lake. Another significant feature is the Incline Village Fault, situated near the northeastern shoreline. Like the West Tahoe Dollar Point Fault, it reflects extensional tectonics, though its slip rate and seismic potential appear lower based on current data. Even so, its presence underscores the distributed nature of strain within the basin. Further complicating the picture is the North Tahoe Fault, identified through geophysical surveys of the lake floor. This fault, along with others mapped beneath sediment cover, contributes to a mosaic of structures that collectively accommodate crustal stretching. While not all of these faults are capable of generating large magnitude earthquakes individually, their interactions can influence how stress is transferred across the region. The broader tectonic context connects these local structures to larger systems. To the west lies the Sierra Nevada Frontal Fault System, marking the boundary between the rising Sierra Nevada block and the subsiding basin and range. To the east, the deformation continues into Nevada, where numerous normal faults define the landscape. Although the San Andreas Fault dominates seismic attention in California, the extensional regime east of the Sierra Nevada represents a distinct and active tectonic environment. Within this environment, the West Tahoe Dollar Point Fault stands out for several reasons. Its length and continuity provide the physical basis for larger ruptures compared to shorter, segmented faults. Its location beneath a deep lake enhances the preservation of geological records, allowing scientists to reconstruct its history with greater clarity. And its proximity to developed shorelines raises the stakes in terms of potential impact. Population growth around Lake Tahoe has intensified exposure to seismic risk. Communities on both sides of the state line have expanded over the past decades, with infrastructure including roads, bridges, utilities, and tourism facilities concentrated near the shoreline. Many structures were built before modern seismic design standards were widely implemented, particularly those dating back several decades. Ground shaking from a magnitude 7 earthquake could exceed design thresholds for older buildings, leading to structural damage or failure. Transportation corridors are also vulnerable. Key routes encircle the lake, often hugging steep slopes or crossing areas prone to landslides. Strong shaking could trigger rockfalls and slope failures, blocking access and complicating emergency response. In winter months, when snow accumulates in the region, these hazards could be compounded by avalanche risk. The lake itself, while a defining feature of the region's natural beauty, introduces unique considerations. Water saturation in sediments can amplify shaking through a process known as liquefaction, where loosely packed materials temporarily lose strength and behave like a fluid. Areas with artificial fill or unconsolidated shoreline deposits are particularly susceptible. Damage to piers, docks, and waterfront properties could result not only from shaking, but from ground deformation and wave action. Monitoring efforts have expanded in response to growing awareness of these risks. Seismic networks in the Tahoe region record small earthquakes, providing data on how stress is accumulating and being released. Advances in underwater mapping technology have allowed for detailed imaging of the lake floor, revealing fault traces, scarps, and landslide deposits with unprecedented resolution. These datasets are critical for refining hazard models and updating building codes. Despite these advances, uncertainties remain. The exact timing of past earthquakes is constrained by dating methods that carry margins of error. Slip rates along the fault are estimated rather than directly measured over short time spans. Interactions between faults, whether a rupture on one could trigger movement on another, are complex and not fully understood. These uncertainties are inherent in the study of geological processes that unfold over thousands to millions of years. What is clear is that the West Tahoe Dollar Point Fault is not dormant. The geological record indicates repeated activity, and the regional tectonic setting continues to drive deformation. The estimated recurrence interval of 2,000 to 3,000 years places the present within a window where another major event is plausible, though not predictable in the near term. The 3 to 4% probability over the next 50 years translates into a level of risk that demands attention, particularly when considered alongside the concentration of people and infrastructure in the area. As mapping and modeling continue to evolve, comparisons with other fault systems provide context. In many regions, faults with similar lengths and slip characteristics have produced earthquakes in the magnitude 7 range, accompanied by significant surface rupture and strong shaking over wide areas. While each fault behaves according to its own conditions, these analogs inform expectations for what the West Tahoe Dollar Point Fault could generate under the right circumstances. At the same time, the presence of multiple faults beneath Lake Tahoe raises questions about how seismic energy might be distributed across the basin. Could stress accumulate simultaneously on several structures, leading to clustered events over a relatively short period? Or does the release on one fault reduce the likelihood on another, at least temporarily? These dynamics are subjects of ongoing research, drawing on both field observations and numerical simulations. The interplay between tectonics and landscape evolution is also evident in the Tahoe Basin. Fault-driven subsidence has shaped the basin's depth, while uplift along adjacent ranges has influenced drainage patterns and sediment supply. Over time, these processes have created the conditions for the lake's clarity and depth, even as they set the stage for future seismic activity. The same forces that built the landscape continue to operate, largely unnoticed beneath the surface. The pattern that emerges from the lake floor is not a single line of weakness, but a system under tension, one that has been quietly accumulating strain across centuries. Measurements of crustal deformation across the Tahoe Basin indicate that extension continues at a slow but persistent rate, on the order of fractions of an inch per year or a few millimeters annually. That motion may seem negligible over the span of a human lifetime, yet over centuries it translates into measurable displacement, and over millennia it becomes the driving force behind basin formation and seismic release. The West Tahoe Dollar Point Fault absorbs a portion of that strain, storing elastic energy in the surrounding rock until it is released in abrupt episodes. Strain accumulation does not occur in isolation. Adjacent faults within and around Lake Tahoe participate in a broader redistribution of stress. When one segment moves, it can alter the stress field on neighboring structures, either increasing or decreasing the likelihood of subsequent rupture. This interconnected behavior complicates hazard assessments. The State Line Fault and the Incline Village Fault, along with smaller mapped features beneath sediment cover, form part of a network where stress transfer is an ongoing process rather than a singular event. Geophysical surveys have revealed that some of these faults extend deeper into the crust than previously recognized, potentially linking with structures beyond the immediate basin. This raises the possibility that a significant earthquake on the West Tahoe Dollar Point Fault could influence a wider area than earlier models suggested. Ground shaking intensity would depend on multiple variables, including rupture length, slip amount, and the direction of rupture propagation. In a scenario where the rupture initiates near the southern end and propagates northward along its roughly 25-mile or about 40-kilometer trace, communities along the western and northern shores could experience sustained shaking lasting tens of seconds. Seismic waves traveling through the basin would interact with local geology in ways that amplify their effects. The lake itself overlies thick accumulations of sediment in certain areas, and these softer materials can enhance shaking compared to the surrounding bedrock. This amplification is particularly relevant for low-frequency waves, which tend to affect larger structures such as multi-story buildings and bridges. Although Lake Tahoe does not host dense urban development on the scale of major metropolitan areas, its infrastructure includes hotels, residential complexes, and transportation links that could be sensitive to such motion. Liquefaction remains a critical concern along portions of the shoreline. Where sediments are water-saturated and loosely packed, strong shaking can cause them to lose cohesion, leading to ground settlement or lateral spreading. In practical terms, this could manifest as tilting or sinking of structures, cracking of roadways, and displacement of buried utilities. Shoreline areas that have been modified through human activity, such as filled land or dredged zones, are particularly vulnerable. The interaction between liquefaction and wave action within the lake could further destabilize these zones during and after a major earthquake. The hydrodynamic response of the lake introduces another layer of hazard. Numerical modeling of basin oscillations suggests that seismic shaking could initiate standing waves that reflect between opposing shores. These oscillations, sometimes referred to as seiche, can persist for extended periods after the initial disturbance. Wave heights might fluctuate over several cycles, with localized amplification in certain coves or embayments. Even a rise of several feet, or around 1 meter, could inundate low-lying areas, damage docks, and disrupt vessels. If submarine landslides are triggered simultaneously, the resulting waves could be more abrupt and concentrated. Evidence for past underwater landslides is preserved in the sedimentary record. Thick, chaotic deposits interspersed among more orderly layers point to episodes when large volumes of material move downslope rapidly. These deposits are often associated with the same time intervals as major turbidite layers, reinforcing the connection between strong shaking and slope failure. The spatial distribution of these deposits suggests that multiple slopes around the lake have failed during past events, not just those adjacent to a single fault trace. Beyond immediate physical damage, the cascading effects of a major earthquake in the Tahoe Basin would extend into systems that support daily life and regional connectivity. Power transmission lines traverse mountainous terrain, and substations located near the lake could be affected by both shaking and ground deformation. Water supply systems, including pipelines that draw from or cross near the lake, could be disrupted. Communications infrastructure, increasingly reliant on interconnected networks, might experience outages if key nodes are damaged. Emergency response in such a setting presents logistical challenges. Access routes encircling the lake are limited, and many segments are constrained by steep slopes on one side and the lake on the other. Blockages from landslides or structural damage could isolate sections of the shoreline, delaying the arrival of assistance. Seasonal factors add complexity. In winter, snow and ice can hinder mobility, while in peak tourist seasons, population density increases significantly, placing additional demand on evacuation and medical services. The statistical estimate of a 3 to 4% chance of a magnitude 7 or greater earthquake within 50 years is derived from combining recurrence intervals with elapsed time since the last major event. This approach does not imply a steady countdown, but rather a probabilistic window that reflects uncertainty. If the average interval is between 2,000 and 3,000 years, and if the last major rupture occurred toward the earlier end of that range, the present could be approaching a period of elevated likelihood. However, variability in recurrence means that intervals can be shorter or longer than the average, and the exact position within the cycle remains uncertain. Comparisons with other normal fault systems in the Basin and Range province provide context for interpreting these probabilities. Faults of similar length and slip rate have produced earthquakes in the magnitude 7 range, often accompanied by surface rupture extending for tens of miles and vertical displacement of several feet. These events have demonstrated the capacity for widespread ground shaking and secondary hazards such as landslides and infrastructure damage. While Lake Tahoe's setting differs due to the presence of deep water, the underlying mechanics of fault rupture are comparable. The role of the Sierra Nevada frontal fault system is also relevant. This larger structural boundary accommodates differential motion between the uplifted Sierra Nevada block and the subsiding Basin and Range. Stress generated along this boundary can influence faults within the Tahoe Basin, including the West Tahoe Dollar Point Fault. The interaction is not necessarily direct or immediate, but over geological time, it contributes to the distribution of strain that ultimately drives seismic activity. Although the San Andreas Fault lies farther to the west and operates under a different tectonic regime, it serves as a reminder that California's seismic hazard is multifaceted. Public awareness often centers on that major transform boundary, yet extensional systems like those beneath Lake Tahoe represent a distinct set of risks. The absence of frequent large earthquakes in the Tahoe region can create a perception of relative stability, even as geological evidence points to the potential for infrequent but significant events. Advancements in technology continue to refine understanding of these systems. High-resolution sonar mapping has revealed subtle fault scarps on the lake floor, some rising only a few feet, yet extending for miles. These features mark the cumulative effect of repeated displacements. Seismic reflection profiles provide cross-sectional images of sediment layers, allowing researchers to trace disruptions associated with past earthquakes. Together, these tools create a three-dimensional picture of the basin's structure and evolution.